neural network architecture, which we were trying to code using PyTorch last time, and you might have seen like a demo today as well, how you train this thing. So I think some parts were remaining from the previous lecture. I will quickly try to cover those today. So this was your full network architecture, which is your CNN network. And as we discussed last time, you need like two functions: the init function, which will define the layers, the forward function, which will define the network, or you can say like the flow of your data into your network. And to define this, you're going to use all the layers you have described in the initialization function. And we were, I think, talking about this initializer in the last lecture when we finished. So I think there were a lot of questions last time. If there is still any doubt or any question, please let me know. And then we will move on to the forward function. So these two are like the conv layers. And then we had like 3 linear layers. So these are fully connected layers. And I think the main doubt was this first parameter in all these layers. So this first parameter is like indication of what's coming in from the previous layer. So you will make use of that to define these parameters. And the second is like how you want to design your network. So I hope this is clear now. And if not, please let me know. Now, the second important part is actually the forward function. You definitely need this function whenever you define your neural network. And this forward function actually describes how your feed forward operation will be performed, or how your data will be flown like in your network when it tries to predict some kind of output. So this X is your input data, and you can have multiple inputs as well. So that's the flexibility which PyTorch provides, and which is actually good. In this case, we just have one input, and this one input is regarding the image for which we are going to perform a digit classification. All right. So now let's look at the first layer. So this self.conv1 we describe in the initialization, right? So that's the first convolution layer, and we are sending in the input image to this conv layer here. And in this conv, then we know that how many filters we have, what's the shape of the filter, then that filtering operation will be applied on this input image. And again, this is not just one image, you will have a batch of image. Okay, so it could be like 10 images or 16 images, depending upon what's your batch size. So all the images are being passed at once. So in this case, let's say the batch size is 16. All right, so then the shape of this matrix here will be 16 times 3 will be number of it will not be 3, it will be just 1, because it's a grayscale image. So 16 times 1, and then the x and y, the resolution of the image, which is 32 cross 32. So it's a 4-dimensional matrix, and that is being passed to the first convolution layer, right? So after this convolution layer, then it will give you like some kind of activation feature activation. It will have certain size. It could be like 28 cross 28 cross 16, I think, if you're using 16 kernels. Then what we are doing is we are passing this activation map to an ReLU activation. So this is like for non-linearity. So F is like just a functional API which PyTorch provides. You can import this. I think there was a question last time what F is. Okay, it's not defined. So F is like a functional API which you'll have to import from PyTorch. And I think for that, you can just write import torch.nn.f. Okay, nn.functional as f. So you can then use multiple functions which are which are present there. So ReLU is one of them. So then this activation, after this activation, again, so that will be your feature map. And then you're passing that feature map to a subsampling layer or a max pooling layer. Again, this max pooling operation, you're directly using on the fly. You don't have to define any layer for this. And so one reason you didn't define this max pooling and ReLU layer is you don't need any parameters actually for these layers. But of course, you can define these layers as well in your initializer and then use here. So these are just being used on the fly. So this max pool 2D is like max pooling in 2-dimensional because of this 2D. And here you can see that the you have two parameters here. So these parameters are going into max pool this function, and this is the shape of the kernel. All right, so the kernel it's 2x2, and you can also pass like this stride, which could be the next parameter. By default, stride I think is 1. So then with this parameters and these activations, when you perform max pooling, your features will be reduced to 14 cross 14 and then 16. Okay, so this is like 3 layers in just one line. I think there is a question. So question from Curtis, is there any benefit of torch.nn.functional versus just using torch.nn? So if you're doing torch.nn.functional, I mean, you're directly importing that particular file, right, or that particular package, and then you can access like all the functions which are present inside this functional. If you use torch.nn, then you are importing like all the packages inside nn that will also include functional. So this is I think this is not specific to Torch. This is like PyTorch thing, how you import your packages. But in terms of functionality, it's the same thing. Okay. Yes. So same function. Yeah, I mean, they will have the same function, right? So this functional is like, this is a package inside your neural network package. So that's like only providing you this subspace, right? Which is inside functional, but this is giving you like a bigger subspace, but of course functional is inside that, so you can use it. I'm not sure whether I got your question. So Curtis, is it clear or you are still not sure? So probably don't worry about this. I mean, again, as I said, this is like, this is not a Torch specific or PyTorch specific. This is something how packages work in Python. So if you know, that's good. If you don't know, then don't worry about it. Just import this torch.nn.functional. Oh, okay. So you are saying that again, so functional is like, yeah, so there is a difference. Again, functionality wise, there is no difference, but it's just like the usage, because nn.relu is giving you a layer. And if you want to define your layer in your initialization, you can define using nn.relu. But if you don't want to define it, directly want to use it on the fly, then you can use like functional.relu. But yeah, they both are the same thing. Is it clear now? Okay, great. All right, so that's your first con layer, the activation, then max pooling. Okay, so then again, this is your second con layer. Again, you define this in your initialization, and you can see that the input was X, and after this layer, the output is also X. And of course, you can use a different variable name. Usually, we just keep the same name, and then again, you can use this X as input here. So the input to this con2 layer is this X, not this X, right? So it's like a continuous flow. This X is going to this, and this X is going to this second layer. And again, it's the same operation. You have ReLU, then you have max pool. And again, the output is stored in a variable X. And again, this is something like, which is coming from Python. It's not PyTorch or Torch specific. That's how the variables work. Okay, you're just overriding like the original variable when you're doing this operation. So one important thing here is that here you specify 2x2, but if it's a square size, you can just use one number 2, and then it's kind of implicit that it's a squared kernel, and you can just extend it to 2x2 if it's 2-dimensional. If it's 3-dimensional, you can extend that to 2x2x2. All right, so again, this is similar layer, but the second layer of your neural network. Then this is interesting. Now what's happening here is, whatever output you got after this max pooling layer, you are trying to actually flatten that, and that's called feature flattening. So what feature flattening does is, and we have discussed this earlier, in convolutional neural networks, you move from volume to volume, right? But in neural networks or fully connected layers, you move from features to features. So those features are flattened. Let's say your feature dimension is 512. So you will have 512 feature dimension, dimensional feature vector. Then fully connected layer, again, you might get like a flattened feature, which could be 512 feature vector. All right. So it's not volume to volume. So those features are called flattened features. And that's exactly what we are doing here. We are converting this volume to a flattened feature vectors. So then this is the helper function which we have defined, and which is trying to actually find how many values we have in this activation feature map, right, X. And then it will try to find that out and just return that number. So then this is X dot view. We had a pop quiz last time as well. What this does, this is just reshaping your tensor. And we have a -1 here. And then this is the second dimension. So second dimension is giving you like the total number of values you have in the previous activation map. And then the first dimension you are trying to figure out automatically. So this is corresponding to the batch size, because your batch size might change. So this will be the batch size, and this is like the flattened feature vector. So I think there is a question. Yes. Functional can't be trained. So functional, it's on the fly, right? And you don't have any parameters. So it's not about whether it can be trained or not. I mean, there is nothing to train actually. Right? If you do have like parameters, then it will get trained, because it's all about, because whatever function you use, it will have to be differentiable, right? So anyways, I mean, whatever activation function you compute, you will compute derivative for this. So it's not that you're not back propagating through this functional. Okay, is it clear, James? So when you say trained, I mean, trained is nothing but it's just having parameters and updating those parameters. So question from Daniel, just curious, do you prefer torch.view? So probably, okay. Do you prefer torch.view to torch.flatten? If so, why? I will say it's like your coding style, both are fine. And view actually gives you more flexibility, right? So it will not always be like you're converting your high dimensional activation map to like one dimensional feature vector. If you're doing that, then flatten is perfectly fine. But view is something you might have to like maybe reduce the number of axes, right, in your feature vector. So view is giving you more flexibility. That's the only difference. Okay, so this is just doing reshaping. We'll go over this function, how it's able to compute like the number of features you have in X. That's coming up in the next slide. Then let's say we did that. Then X is like a flattened feature vector with two dimensions. The first is batch size, the second is number of features. Then we just pass them on to like the fully connected layer. We define FC1. Then that's being passed to the second fully connected layer. And then that's being passed to the third fully connected layer. And this will give you the predictions, because the output of this FC3, you know, it was like 10 neurons, right? Because we had 10 classes. So this is your fully feed forward operation, which will be performed, and your data will flow from the parameter over here and to each of these layers sequentially. All right. And then finally you return this. So this is your input and this is your output. So this is your full network. So this was the helper function. And here you can see that how we are trying to figure out like how many features we have. So this is like making use of slicing. So you can see that X dot size is going to give you the shape of this feature vector. So in this case, it will be the batch size. Let's say the batch size is 16. Let's fix it to that. So the shape of this will be 16 cross, then number of channels, I think it was 16, and then the resolution, that was 6 cross 6. Okay, so that will be the value stored in X dot size. but we are trying to slice it. So we are not taking the first value, but all the other values, which means that we will ignore the number, the batch size, right? And then we only include like the three-dimensional feature vector, which is like the depth and x and y, that will be like 16, 6, and 6. So then you can see that this will be a list which will have these three values, 16, 6, and 6, and we're just iterating over that and trying to multiply. So we are just multiplying 16 times 6 times 6, and that's actually like the number of features we have in our feature map, and we are just going to return that. So the key is just to ignore the batch size. All right. So that was like how you define your neural network. I think there is a question from Brandon. So a fully connected layer would be that last slide. So yeah, your fully connected layers, you have three fully connected layers, right? FC1, FC2, and FC3. So you have three fully connected layers in your network. Okay. So Daniel, your doubt was clear or not? You didn't confirm. And also James. Okay, all right, that's good. So now you know how to define your network. Now let's go over like the training procedure. So the first step was defining the network. The second is like you will have to iterate over your data set. So you will get like a batch of it and train your network, do all the things you want. So let's spend some time on like how you can process your data. And from experience, I can tell you like this is the most time consuming step in your whole network training. So I will have to say, if you are good in coding and you have a experience like how to how to define your networks, and you don't have to spend too much time in, let's say, hyperparameter tuning, then 90% of your time is going to be like spent on this data pre-processing. So it's really important, and it takes a lot of time. So for computer vision or for images and videos, we have different libraries which we can use. So we have Pillow, we have OpenCV, and again for audio we have some libraries which you can use in Python, and we have for text as well. Okay, so the idea is, in this step, basically what we have to do is all your data will be on your disk, right? Saved somewhere in some kind of format. So if it's images, then they will be like maybe JPEG files or PNG files. So what this step is going to do is you're going to load that data from disk into memory. So first what you will do is you will load them maybe as NumPy arrays. All right, and then you will have to convert them into tensors, which can be used in GPUs. And you know how to convert NumPy arrays to the torch tensors. That's not difficult. It's all about like getting them into correct format, which your network is actually expecting. All right. Question from Brandon. So if you, okay, I'm confused. Only one fully connected layer, would you include max pooling and view? So Brandon, there's some typo. I didn't get your question. One fully connected layer, would you include max pooling and view? So you are saying that if you have only one fully connected layer, will we need max pooling and view? So view you will definitely need, because that's actually flattening your feature volume to a feature vector. Because fully connected layers take like a flattened feature vector, right? And your CNNs work on volumes. So we'll have to convert those volumes to a flattened feature vector to be able to use fully connected layer. So whenever you're transitioning from convolution layer to fully connected layer, you definitely will need a view. There are some special cases, but no special cases. I think you will always need that, or you can use just the flatten function. All right. Max pooling, that depends. Like if you want to reduce the number of values in your activation map, you can use max pooling. But if you don't want to reduce the memory consumption, you don't have to use max pooling. Okay, good. So another question from Ruchia. In fully connected layer, in forward function, why are we not applying railway activation function for F3? Okay, let me see. Okay, so that's a good point. So you can see that we have activation ReLU here, we have here, so that's introducing nonlinearity. Now, this last layer is actually making some prediction, right? And we want this prediction to be of a certain range. So in this particular case, we are doing classification. And depending upon your loss function, you may want to normalize your normalize the values in X. So in this case, if you are, let's say, using cross entropy, so the cross entropy function, which is there in PyTorch, it automatically does the softmax normalization. All right, so softmax, if you have heard about it, it's fine. If you're not, don't worry, we're going to cover that later in the course. It just tries to normalize your values and tries to make them between 0 and 1, because that's what we expect, like when we use a cross entropy loss function. All right, so that's one way. So in that case, therefore, we don't need to use any activation here. The other thing is you can use activation, maybe a sigmoid here if you want to restrict the prediction between 0 and 1. Or you can use tanh if you want to restrict between -1 and 1. So if you think about this, after this applying activation, we only need, because if you want the output to be in a specific range, because it's not going to introduce any nonlinearity or something, because after this, you're not doing any learning. It's just the prediction. So scaling your values it's not learning. Okay, so Ruchia, did that answer your question? Okay, let me know if it's not clear. Okay, so that signifies the output. Yeah, this is the output. So whatever you're returning in the forward function, that's the output of your network. In this case, the output will be like 10 probabilities, 1 probability for each digit, because we have 10 different digits, right? So this is the output. After this, we are not performing any learning. All right, great. So let's move forward. Okay, so for visual data, I think Torch Vision is a library which is there in PyTorch, which is actually very helpful. And this is how you can import this. Just to import Torch Vision, then you have torchvision.transforms. So these are the transformations which are already provided by the PyTorch library, and later we'll see like how useful these are. So transforms are required to maybe resize your images. Let's say your actual images are maybe 200 cross 200, right? But you want your images to be 128 for your network. So this transforms allows you, provides you that flexibility so that you can resize your images and also perform like a lot of other data pre-processing tasks. So to load your data, again, we have special APIs provided by PyTorch. And compose is one of the function which actually provides a list of tasks which you want to perform on your input data. Okay, so let me actually quickly go through this. All right, sorry about that. So what we are doing is we are just trying to, as the name suggests, compose. We are just trying to list like the set of operations which you want to use in our, on our data. Okay, so the first one is transforms.toTensor. So this means that whatever data you have in your NumPy arrays which you load from disk, it will automatically be transformed to torch tensor. So that's why we have this toTensor, right? So this operation will be applied on all the images, all the videos. Then the second operation is the normalization operation, which says that so I think this is the mean and this is the standard deviation. But again, it doesn't matter. I mean, you can look at the API what it actually does. So it will normalize your data. So if you want your data to be like in certain range, you can use this function. Okay. So then if you have composed these transformations, then you don't have to perform these manually like in each of your data samples. it will be automatically done. And the second thing is like you have to define your data set. So this is like the way you define your training set. And again, so this is something CIFAR10, this is provided by PyTorch. This is a well-known data set of image classification. So this is CIFAR10 because there are 10 different classes. It's just the name of that data set. And this root is just saying that where all those images are saved. And these are just some parameters. And again, so this is something like you're using an existing data set which the PyTorch framework supports, but it doesn't mean that you can't use your own data set. All right. So then the train is true. It means that you are passing like a parameter. You're saying that only training images should be loaded. Download equals to true. Again, this is a parameter. If it's not there in this location, it will be downloaded from the link which you will provide. And then the transformation. So this is the important step. Whenever you define your data set, you will pass this transformation parameter, which is like this transformation which you defined previously. So when you say that, then what's going to happen is all these transformations will be automatically performed on all the images which are being loaded through this data set. Okay, so that's how you do that. Then, so that was a transformation, that was the training set. And again, you can, as I said, you can define your own training set. All you have to do is just maybe it could be like your list of videos, or it could be your list of images. All right. And then this is how you define your data loader. And I will explain what data loader is. And it plays a very important role in your network training. So this is the way to define data loader. So the input is the train set, which you defined right over here. Then this is the batch size, which you know, like how many samples you want in each iteration. Then this shuffle parameter is like you want to shuffle your training samples, right? And what it does is it's kind of providing more variation into a training. So let's say you have 1,000 images. So if you don't shuffle your training samples, what will happen is the same set of 4 images are always being sent together, right? Then the training will be kind of restricted because it's always seeing those 4 images at the same time. But if you will, and so that's one thing, and also the order in which the network will see those images, that will not change. But if you shuffle your list, then every time after each epoch your network is done through the list, it will randomly change the order. Then that will make sure that the order of the images is different. And also like the set of images you send as one batch, that will be different. So that adds like more variability into your training, which helps the training process. Now, this is also very important, but not from this course, but I think you should know this. So number of workers is something like the number of processes you will invoke to load your data. And this is important because when you are training your network, the feed forward step is not like time consuming because it's being performed on GPU, right? It's pretty fast. Once you have your data ready, it will be performed pretty quickly. Most of the time, your network is actually waiting on loading the data from disk, because you know that disk IO is very computationally expensive, right? So to do that, and that's why this data loader comes into picture, it allows you to load your data separately and detach that from your actual network training. So what happens is you have these 2 tasks running in parallel. The first task is just doing the feed forward. So it's training your network, feed forward, computing gradients, and updating weights, right? So that's one step. The second process is just loading data from disk. And this number of workers is like how many workers you want to load your data, which can actually load the data, right? So if it's 2, it means like there are 2 parallel processes which are loading data from disk. And then what happens is, as soon as this GPU process is done, it will take the data which was loaded like in parallel and then keep fetching that. All right, so there is that connection between those 2. So the first is data loader, the second is actual network training. Now, similarly, you can define your test set, and it's the same thing. You will have to perform the same set of transformations. This is also fine. If it's not there, it will be downloaded. Train equals to false means it's trying to load the testing data, not the training data. And this is pretty important here. The shuffle equals to false because you don't want any shuffling in your testing data, right? It doesn't matter because you just have to do like feed forward. So it doesn't matter like what's the order of your data. And again, batch size and number of workers. Okay, so question from Brian: is .data a local folder or placeholder for site on internet? Yeah, this is the local path where that data will be stored or where you have stored your images. Okay, so that was all about data loading. And I think this is a bit complicated. If there are questions, please let me know. I will try to explain them. But this, I think we have already provided you in the sample code. So from assignment point of view, you don't have to worry about this. But if you have any further questions, please let me know. Okay, so let me continue with the second part. All right, so this is just like continuation of the previous slides. Okay, so that's how you load your data. All right, so now what data loader will do is, as I said, you will have parallel process, which is loading the data like in terms of batches, and then those batches are being passed to your network and loaded into the GPU. So now let's see, once we have that batch ready, how that's processed through the network. And it's pretty simple. You have the forward function. The batch will be assigned to this parameter X, and all these operations will be performed. And then this network will return this value X. So this will be done for like each batch. Okay. So that's called feed forward. And once we have the network's prediction, we'll have to compute the loss. Okay, so for loss, we need like the output of the network, and then we also need the ground truth, which is called the target, which should be the actual target. And we use these two to compute the loss value. So this neural network package actually provides a lot of loss functions, which we can simply use. So we have cross entropy, we have MSE loss. And let's see like a simple example. So let's say we have this network net, which we defined earlier. Now we will pass the input. So this is like one batch, and output is like the value which your forward function is returning. And let's say we created the target randomly. So this is the ground truth, but of course you will load again this from disk because we'll have the ground truths. So in this case, we are just creating dummy targets. So we are creating 10 targets, and we are just changing it view because we are assuming that we have a batch size of 1. Okay, so that's a 1, and then this will have 10 values that you know by now. Then, okay, so how to define your loss function? As I said, this neural network package provides like a lot of loss functions, and you just call that function and define that as criterion. Okay, so then once you have defined this, this can be used to compute the loss, and it's pretty straightforward. You pass like the output of the network and the target, and then this criterion will compute the loss based on whatever function you use. And of course, you can write your own loss functions as well. You doesn't have to rely just on the PyTorch functions. Okay, because you have the output, you have the target. I mean, it's up to you how you want to compute this. This could be as simple as just subtracting these two values, right? So it's totally up to you. So then this is going to give you the loss value. That's how you compute the loss. Now, the second thing is you will have to compute the gradients and perform backpropagation to find the gradients for all the parameters, right? So that's the most complicated step in network training. And the good thing is we don't have to worry about it. We just have to do loss.backward. So once you have the loss, just call this function and all the gradients will be automatically computed. PyTorch is doing that for you. Okay, so that's pretty cool. And then once you have the gradients, you can just update the network weights. All right, so to update the network weights, again, you'll have to define the optimizer, how exactly you want to do it. So we saw like a lot of variations. We saw stochastic gradient descent. Then we saw that we can use momentum as well. So let's say, and there are of course different optimizers. The basic one is the stochastic gradient descent. And the way you define is you just call this function and you're passing all the parameters you have in your network. So net was your architecture, right? You defined it like this. And net dot parameters, what it's going to do is all the trainable parameters you have in your network, like the kernels or the biases or the fully connected layers, weights for those, they will be returned by this function. So you will pass those parameters to SGD and you will define a learning rate. So in this case, it's 0.01. So again, this is a hyperparameter which needs to be optimized as you train your network. So this is again something which you'll have to spend a lot of time to make your network training stable. Okay, so this defines your optimizer, and now let's see how you can use this. So this is fine. You don't have to actually do this, but this is like a step which is just saying that, okay, just make the gradients 0, because you do have a variable like which will store the gradients. So what it's doing is it's just making all the gradients 0 to begin with, but you don't have to perform this task. So then you pass the batch as input to the network that will make the prediction. You compute the loss. We discussed this in the last slide. You do the loss dot backward. So that's going to compute the gradients. And then you just use the optimizer you defined and do the step function. So whatever gradients were optimized, it will just update all the parameters in the single step. Okay. So if you think about this, this is the actual training. In fact, these two steps, because this is computing the gradient and this is updating the network weights. But these are the like most important thing, and you don't have to do anything about it. It's just like the same steps. This is not going to change like even when you change your network. Okay. So any question so far? So then this is like just one iteration, right? So you take a batch and then you will perform this step. Then you will get the second batch, will perform this step, and you will get like all the batches which you can from a training set. So each iteration is like, it's called one iteration. So depending upon the total network size, the total number of samples you have in your training set and the batch size, the number of iterations will vary. And that is actually the next pop quiz. And one epoch is like when you go through the complete training set once, and then you keep repeating that over time. Okay, question from Mustafa. Output equals to net input is the forward propagation step. Yeah, that's true. So that's just one feed forward step. You have a batch and you do the feed forward. So input is like storing one batch of data. Question from Anshuman. Please reiterate calculation of linear layer input parameters. Calculation of linear layer input parameters. Okay, you mean like when you are defining the linear layer, or like the network weights? Oh, okay, I understand. All right, let me go back. So probably you're talking about right, this thing. So let me go to the initialization actually. Oh, that was a different slide. Just give me a minute. Okay, can you see my screen? I just shared the other one. Okay, good. So I hope you understand. So this is the input resolution, and as you move forward, like in the convolution, you will have, so this is the last convolution layer, right? And it's giving you a feature shape of 16 cross 10 cross 10, right? Just ignore like the by the number are 10, just assume that okay, it's 10, because that you can compute like using the formula. So it means that you have like maybe 16 kernels in the previous layer, and 10 cross 10 is again, it will depend upon the kernel size in the previous layer and the size of the activation map in the previous layer. So let's say we had something, and in this particular layer we got 16 10 cross 10. Then this subsampling is actually just max pooling. So max pooling will not change the depth, right? So 16 will still be 16, and 10 cross 10 will go to 5 cross 5. Now, if you think about this, this is a volume. It's a three-dimensional volume, and its shape is 16 cross 5 cross 5. Now, how many values we have, how many feature values we have in this volume? So we can just multiply 16 by 5 by 5, right? So it means that it's like roughly 16 times 25, right? So that many values in this layer
is 400.
Right? So yeah, so that's 400. So if you have to create like a fully connected layer here, then you need to understand what's the size of the input feature vector. Then only you will be able to create like all the weights, right? And in this case, you will have to flatten this, and that will give you 400 different values. And therefore, the input size for this particular layer will be 400. And 120 is something like the number of neurons in the current layer. We need that 400 because that will define how many parameters you have in this fully connected layer. So the number of parameters will be 400 times 120, because each neuron will have to be connected to each input data point. Right, so that function, the helper function which we defined, was exactly doing that. It was just trying to find out how many values or feature values you have in your input feature map. Okay, all right, good. So that's clear. Let me quickly do the new share. Okay, question from Roger. Can you just go over one iteration concept? Sure, yeah. Okay, so the way training works is you have a certain number of samples. Let's say you have 100,000 samples, right? So that's your training set. Now we have discussed, we can't train like using all the samples at once. Therefore, we create batches. So therefore, we have a parameter called batch size. Now, batches is like you pick that many samples. So let's say we have a batch size of 16. So what you will do is you will select 16 samples and do a forward pass, compute the loss, backpropagate, compute the gradients, and update the network parameters. So that whole process using one batch is called one iteration. Then again, you will pick like another batch, do the same process again. So that will be second iteration. So in each iteration, you are actually training your network. Right? So then you will keep doing that until you are done with all the samples in your training set. And that is called one epoch. So one epoch means you have seen your training samples at least once. So once you're done, then you will just repeat this whole process again. So that will be your second epoch. Is it clear, Ruchia, now? Okay, good. So then let's see where we were. Okay. Yeah, so we had this pop quiz. So let's quickly go through this. So the question is, you have 80,000 training samples, all right? And your batch size is 100, which means that you can train like only using 100 samples at once. So that will be your one iteration. And then we were training our data, and we figured out like each iteration is taking 30 seconds. Okay. Then the question is like how many hours or how much time it will require if you want to train a network for 3 epochs. So question from Matt, is one batch taking 100 seconds? one iteration is taking 30 seconds. So yeah, so one batch is taking 30 seconds. I think I was muted. So let's do the math here. So we have 80,000 samples, right? And batch size is 100, which means that one epoch is like going over like each sample here, right? So we can just divide 80,000 by 100. So we'll have that many iterations for the single pass, and that's 800. Okay. So it means like we have 800 iteration. Then it's saying that each iteration requires 30 seconds, which means that 800 iteration will require like 800 times 30 seconds, right? You can just multiply these two, and then that's one epoch. So for 3 epochs, just multiply that with 3. So the answer will be like 3 times 30 times 800. And I think that's 40 seconds. Is it right? Because most of you answered 20 seconds. Is 40 wrong?
Say hours. So
Oh, okay. It still says 40. Why?
each iteration was 30 seconds. It changed.
You said. Ah, okay. So 20. So 20 is the right answer. Okay. Good. That's my bad. So that's 20 years. All right. So I hope this is clear. So yeah, most of you have answered correctly. If there is any question, let me know. Sorry about that. Okay, so now let's go through like the full training steps. The first is, like you define your architecture, then just use that class to create a instance or an object of whatever you want to call that. If you're coming from C++, it will be maybe an object. And so you create an object of this type of class, which is like your architecture, where you need 2 functions, the init function and the forward function. Those 2 are the only requirements. If you want to define those 2, you will get some error. Then you define your data loader. Okay, so all these parameters. So you have to define your train set. You'll have to define the batch sizes, and these are just the hyperparameters. Then you define your loss function or the criterion. So let's say we define cross entropy loss, which we will need for classification. Then the other important thing is the optimizer, and that's how you can define optimizer. I don't think this line is going to change. Whatever network you define, you can just directly use this, and even you can directly use all these. It's just like you'll have to define this train set differently depending upon it's your customized data set or you're using an existing data set. And again, SGD you can change to like any other optimizer like Adam or something else if you want. Okay, so the standard code will be something like this. So this for loop will be like each time you go into the for loop, it will be your one epoch. So in this case, it's two. It means you want to train it like for 2 epochs. So this is just some variable for you can store different things here. That's fine. Now, so there's the outer for loop for number of epochs. This is the inner for loop, and this is for number of iterations. All right. So this train loader, you can directly use it, and PyTorch will automatically give you batches, so you don't have to worry about it. So that's the beauty. So once you have defined that data loader, it's going to do that. So then it means that every time you go inside the for loop, you will have one batch in hand, which will be stored in data. And then you just need the training code for that particular batch. Okay, so let me, and so once you're done with like one batch, then that's it, and your training is done. So this for loop will repeat like for all the batches, and this for loop is going to repeat for like the number of epochs you want, and that's it. Okay, so that's the basic structure which you will require. So let's fill in the these spots here. So that's the only thing which we have to do. So the first thing is you will get the inputs which is stored in the data, and in this case you have the input. So this is the images. These are the images, and these are the ground truth, the labels. And if you are using existing data sets, let's say like ImageNet or CIFAR, so it will be, you don't have to do anything. You will automatically get inputs and labels. But if you are writing your own data loader, which you might do not for the programming assignment, but for the project you might have to do. So then you'll have to make sure that when you write your data loader, you return these two values, inputs as well as labels. And of course, we'll provide you some sample code, template code for that. So again, don't worry about that too much at this time. Okay, so once you have your input and labels, then again, this step, you don't have to do it. We can skip this one. So these are the most important which you should know. So you will do the forward pass, you will do the backward pass, and then you will optimize. Okay, this is the forward pass. You define the net, pass the batch, the inputs which we'll get from data, right? And that's going to give you the output. That's a forward pass. Then you compute the loss using criterion, the loss you have to find, outputs and labels. And again, labels is coming from your data loader. So this is the backward, we have seen this. Then this is the optimization step. And that's it. And these are like statistics if you want to debug or something. Okay, I won't go over these. This is fine. And once you're done with the training, then you can just save your train model. So this is one way to save. There are other ways as well. You can just follow this one. So what this does is it will try to save like the architecture as well as like the weights which you have learned. And then you can later on load these weights and use this for inference. So testing, again, it's pretty simple. You use the test loader, which we defined earlier. And this test loader will, of course, not give you the labels. Okay, it will give you the labels, but you don't need it like for forward pass, right? Because you're not performing any training. So you just iterate over this test loader. You can keep doing next. Next, it will keep giving you batches, and you can pass those images to the network. And this net is like, again, the architecture you have defined, but this one doesn't have like the weights which you train. So we'll have to load those weights, all right, from the path where you saved it. And this will ensure that now you have the correct weights which were actually learned. And then you just keep forwarding like these images. Again, this is just a forward pass, and it will be your predictions. And you can use labels and outputs to actually compute the evaluation metric. It could be accuracy, it could be precision, whatever you want to do. So you have the ground truth, you have the prediction, you can do whatever you want. Okay, so this is fine. It's just trying to figure out like what's the maximum prediction. Now, everything I showed you till now, you were training on CPUs, because we never talked about GPU, right? So as I said, your PyTorch tensors you can use on CPU as well. but we are interested in training on GPUs because that will be much faster. So again, that's pretty trivial. You first have to define your device. And again, if you have GPU, then you will get it, right? It's just checking if CUDA is available. So this actually checks whether you have a GPU, functional GPU or not. So if it is there, it will just assign a device ID to that ID to that. Sorry, and if it's not there, then it's just going to use the CPU. And what you'll have to do is you'll have to transfer your network to the GPU device, and that's the function you use for that. Okay, and then you'll have to shift like all the data to GPU as well. Okay, so whatever data you're going to pass to this network, you just do .2 and the device ID, and this is just sending in like the labels to device. So now these this data over here, this is not on CPU. Now this is on GPU, and then you can pass this like to your network, and the rest of the steps are almost similar, no change. So if you want to use GPU, you just have to perform these 3 steps. Figure out if you have GPU device or not, find the ID. If it is there, just transfer your network to your GPU and transfer all the data to GPU. That's it. Then the other things will be automatically taken care of. Okay, so I think that's all I have for today, and we are right in time. Let me see. So question from Curtis: how many workers should you assign if you are using a GPU? And that's a very good question. Sometimes we struggle to find that out. You'll have to do some optimization. So the ground rule is the number of CPU cores you have in your server, you should use that many. So if you have 2 cores, use 2, and assuming that you don't want to use those cores for something else, right? So you don't want to overload your system. And the more is the better, but it should be like you should have that many cores. If you have only 2 cores and you use 8 workers, then it's not helping, because essentially you are just using the same cores and your workers will be in queue, right? So it's not going to help you. So it depends on how many CPUs you have. Then a question from Sayed: can we train properly on AMD Radeon GPU? Yeah, I'm not sure. Ideally, you should check like if you have proper support for that GPU, because most of this depends upon like the CUDA library. So you'll have to install that CUDA library, and if you have a proper support for this particular, again, AMD Radeon GPU, it should work just fine. But if the CUDA version is not supporting that particular GPU, it's hard to say. Okay, but most of the like recent GPUs, we do have CUDA support, so that shouldn't be an issue. But some of the older GPUs, sometimes it's troubling. Question from Stephanie. I said, okay, so Stephanie, probably just write me an email and copy Tao. So that should be fine. We'll take care of that. So question from Shribo: did that before use RX 580? Okay, so I didn't get that question. Probably you're saying that it will work. Question from Sayed: should we consider CUDA cores when selecting workers? It has nothing to do with CUDA cores. It depends on like on your hardware, right? If in your hardware you have that many CPUs, you can. So it's all about parallel processing, right? So if you have just one core, then it doesn't matter if you use 100 workers. All the workers are going to use the same CPU, same core, and they will be in queue, right? So you're not speeding up the process. But let's say if you have 5 cores or 5 CPUs, then if you define 5 workers, so then each worker will get its own CPU, right? They're not waiting for each other. So that's the bottom line. Okay, so Sayed, I think that answered your question. So question from Amelia: where can we see the sample code just in web courses files? So yeah, the sample code when we have shared like with the programming assignment, right? For the assignment, that should be sufficient for you. But for your if you need like a data loader code for your project assignment, we will cover that later on in the course. So I will say don't worry about that now. Okay, question from Sarah. If CUDA isn't supported on a device, it would be better to just use Eustace. I'm not sure what Eustace is. Probably an alternative to CUDA, or yeah, Sarah, I'm not sure about that. But I can figure it out later. Like if you want that, just drop me an email. Okay. Question from Tristan. We don't need a good GPU for assignment fun. Yeah, for assignment fun, you don't need a GPU at all. You can just run on your CPUs as well, because that's a pretty small network. Okay, question from Sean. Is the information for how to access the GPU clusters? Okay, so yeah, sorry, I forgot that. Thank you, Sean, for the reminder. So if you go to the course webpage, go to the schedule, then just before the today's lecture, you will see like a tutorial on HPC cluster. So go through those slides, go through that video. That will give you like, I think, a very good understanding of how you can use the GPU cluster. So we have started distributing the keys or the credentials. If you need one, just let us know and we'll pass it on to you. Okay. So Sean, you can check there. If you couldn't access it, please let me know, but it should be there. So question from Victor, regarding the programming assignment reports, are there any guidelines we should follow? Yeah, I mean, there are no specific guidelines. Just try to include like whatever has been asked for, like the details and the plots and all those. Just try to include all those, and I think it should be fine. Question from Michael, could you explain what is supposed to be in output.txt? Couldn't hear what you said. Okay. So you are seeing like the print statements, right, in the code. So whenever you run that code, you will have some output. So just copy paste that output to output.txt. It's just like your std out. Is it clear, Michael? Okay. So question from Amelia, where can we see the sample code? Is it just the code? Yeah, that's the only code you have. No, it's not something else. It's the sample code which is there like with the programming assignment, that zip file, because that's sufficient for you to do the programming assignment one. And of course, if you need like the code which was used in the tutorial today, just let me know. We can release that as well. Okay, so I think those were all the questions. If you have any further questions, please do let me know. You can always reach out to me via email. Okay, so let's end it here. Thank you. Bye.